Hello everyone. So this will be our last video about the culture and history of chemistry. And today we will discuss about a topic that is titled like nuclear reactions. And we will cover topics of the new transmutation, artificial radioactivity, fusion, fission, and atomic bombs. But as an introduction, I also would like to discuss that when we started this series of videos, at the beginning we were talking about alchemy and this alchemical dream of transmutation, which they pursue to produce gold from cheap metal. So they wanted to do a transmutation of elements that, as we discussed in previous session, it was not possible given that most of the chemical reactions that we use and that they use in those times, they have an energy that is not enough to break or to change the structure of a nucleus. Therefore, with the topics that we discussed in previous week about radiation and how there was this emission of alpha particles or beta particles and these energetic particles, then with the discovery of these particles, it is now possible at the beginning of the 20th century to achieve what is known like nuclear reactions and make through this alchemical dream of changing between elements through a nuclear reaction. So to say it in more simple terms or in like a simple definition is that a nuclear reaction is the rearrangement of protons and neutrons of the atomic nucleus. And for this, I would like you to recall what we discussed as the Sodus rule. Depending how you make this rearrangement, then you are able to move in the periodic table to the right or to the left. So remember that in the periodic table, we have all these elements arranged according to the atomic number. So when you add, for example, a proton to a nucleus, then you are moving to the right. And then, like a first example of a nuclear reaction, it was shown by Rutherford, who demonstrated that alpha particles could knock protons out of nitrogen and merge with what's left behind. And he did so in 1919. So he made a nuclear reaction between nitrogen 14 plus helium 4 that we can consider it like an alpha particle. Remember that alpha particles are 2 protons plus 2 nucleus. So it matches with what we define like helium or the nuclei of helium. So when you knock this alpha particle with nitrogen-14, he discovers that what is produced is a proton plus oxygen-17. So through this reaction, he was able to demonstrate this, what is called like the new transmutation, or a nuclear reaction, the first nuclear reaction. However, these type of reactions that were developed and demonstrated by Rutherford, they had a limitation in energy, on the energy which is given by the radioactive element. When this radioactive element is producing the alpha particle, for example, the reaction which can be achieved through with this alpha particle is given by the energy that is carried on the alpha particle. So in 1929, an English and an Irish scientist, one of them is Cockcroft and the other is Walton. In 1929, they designed the first accelerator, and this is so to give extra energy to the alpha particle and enable another types or other nuclear reactions. And then they give the example of a reaction between a proton or hydrogen 1 plus lithium to produce helium-4, two particles of helium-4, which is also surprising. Another example of nuclear reactions. However, this designed by Douglas and Thomas, it had a disadvantage, and is that the device was designed in a straight line. So at the beginning, it is useful, and they could run this type of reaction, but to gain more and more energy, then it will require a very long system, let's say, because of the straight line path on which was accelerated the particles. An improvement, a significant improvement, was taken by or given by Ernest Orlando Lawrence, who designed what we know like the cyclotron, and he did that design in 1930. What he did is that now the particles, they were not accelerated in a straight fashion, but he induced a magnetic field, an alternating magnetic field with an electromagnet, and he was able to do this acceleration process in a spiral way. So that's why the name of cyclotron. So the particles were accelerated in this spiral fashion. Therefore, for example, in the device that he first designed, it is said that he could carry the device in his hand, and the price of in money, the price of this design, when he built it, it was only a few dollars, like $25, they say. So with this design, he was able to achieve high energies for the achievement of nuclear reactions in a cheap manner, at least at the beginning in these prototypes. And he was able to induce new chemical or nuclear reactions. By his work with the cyclotron, by the design of the cyclotron and the work that was achieved with this device, he was awarded in 1939 with the Nobel Prize. And not only that, but he also was working in collaboration with his brother for the application of this type of isotopes that were produced during these nuclear reactions for medical purposes. And another topic which is included in his Nobel Prize is for his work with what is known like the artificial radioactivity. To talk about artificial radioactivity, we should know that it was a couple of husband and wife, the first who who discovered this process. And what they did is that in 1934 they were able to produce phosphorus 30, which is an isotope of phosphorus which does not occur naturally. And what they did was bombarding aluminum-27 with alpha particles, and they saw that after this bombardment the sample remained radioactive. And when they checked, then they discovered that effectively it was phosphorus 30, which is not natural occurring compound, and it has a very short half-life of only 14 days, which explains why it's not so easily detected in nature, or why it is considered like not natural. A consequence is that since that moment and since 1932, over 1,000 isotopes not occurring in nature have been produced, and all of them are radioactive. So this opens the door for a new set of uh, opportunities for applications, for example. And the applications vary vastly. For example, probably the most known isotope is carbon-14, which has a half-life of over 5,000 years. And this carbon-14 is produced in the atmosphere by cosmic rays and nitrogen. So cosmic rays are produced in the outer space, and they consist mainly of positively charged particles. And as you know, this carbon-14 isotope is used for archaeological applications and for history, for to date articles or remains in historical periods of civilization, for example, or biological samples in different periods of time. So what is important about this compound is that, as I said, it is produced in the atmosphere, and the living organisms in the respiration process, they uptake this isotope. Carbon-14 is incorporated into the tissues of the living organism, and once this organism dies, then it's not longer incorporated. It cannot be incorporated more to the organism because the respiration is over. So by tracing or by measuring the content of this carbon-14 in an organic sample, it can be estimated when was the period in which the organism was living. And then this is an important application that is quite popular, and everyone heard about carbon-14. But not only that, I mean, there are other isotopes that have been used for the analysis of chemical reactions and to trace the mechanisms. So in a molecule, it can be inserted an isotope of a given atom. By tracing how it is flowing through the reaction, then it is possible to trace or to deduce what is the possible mechanism for a complex chemical reaction. One example of that, it was the study of photosynthesis by a chemist called Melvin Calvin, who was using isotopes to reveal what is the mechanism of this process. And as I said before, then radioactive isotopes like phosphorus 30, for example, it has been used for the investigation of therapeutic purposes. And for example, by the brother of Lawrence, I mean, yeah, he's also Lawrence, so John Lawrence, he he was one of the pioneers to use these isotopes for medical applications, and they did so. So Ernest and his brother, they did so because at their time, it was much easier to achieve or to get some funding, some resources for investigation if you apply like for medical applications than for physics itself. So it was a way also to be able to get more money. and of course to advance and to produce also important results in medicine. With the development of the cyclotron and all this knowledge about the subatomic particles and how to increase the energy for the effective bombardment of atoms, then other application was related to the discovery of new elements. And we should remember that still at this time, at the beginning of the 20th century, still there were some gaps in the periodic table that they were not discovered yet. The elements, they were not discovered yet, even though they were predicted. So the first, let's say, that could use this radioactivity for the discovery of other elements in the 20th century was Lawrence, who did mm, a bombardment of molybdenum using nuclei of hydrogen 2. And with this, he got a sample which was radioactive, but he sent the sample to one of his friends who was an Italian-American physicist called Emilio Segre. And it was Segre who analyzed the sample and discovered that, in fact, this radioactive sample contained uh, a new element with atomic number 43. And this was, he gave the name of technetium, which means artificial, because it is not found in nature, or if it is found, it is in such a small amount that, okay, the name was proper, like it's an artificial element, let's say. After this, soon, other elements were discovered with atomic numbers 87 and 85. And finally, in the 47, there was still the last gap in the periodic table, and it was discovered an element with atomic number 61 with the name promethium. So, but then the scientists, they were curious, like if now they could do bombardments with positively charged particles, it means that they would be able to create even new elements. So completely new elements and go even beyond uranium, because at the time it was thought that, I mean, or it was known that uranium was the largest atomic number in the periodic table. But if you could somehow add protons to the atom, then finally you will end up increasing in atomic numbers, and therefore you will be able to create new elements. And this is so, and so they started to do this, and we will talk about it in the next slide. But what is more important now is that if you remember from the previous lecture, it was in this time when the neutron was discovered, and the first who made bombardments with neutrons, it was an Italian physicist called Enrico Fermi. So he did this neutron bombardment, and it had very important consequences, for example, for the discovery of, or the development, the development of the nuclear bomb. In his experimentation with neutron bombardment, Enrico Fermi found that what is required for the effective nuclear reaction is that the speed of the neutron, which is used for the bombardment, is in the same order of magnitude like the vibrations of the atoms or the molecules that used like a target. For that purpose, he used what is now called like a mediator, on which the neutron is slowed down by the interaction with other molecules. Like he used, for example, water or paraffin, and through this medium, the nuclei, or the neutron slows down its velocity, and it could react much easier with the nuclei of the target. Uh, and this is another advantage of the neutron bombardment. And the thing is that if you do a bombardment with, for example, an alpha particle, you should remember that the alpha particle is positively charged due to the presence of the two protons, but the target, the nuclei, which is the target, it is also positively charged by the protons of the element. Therefore, when you want to do this bombardment using alpha particles, you require a very high energy in order to be able to overcome this repulsion experienced by the alpha particle, positively charged, and the positively charged nuclei of the target. And this is different in the case of neutron bombardment because the neutron has no charge, and therefore it can approach much easier to the nuclei of the target. Uh, so this is the main advantage of the neutron bombardment. Another thing that was discovered after these nuclear reactions with neutrons is that typically the new isotopes which are formed, they are also radioactive and they break down by emitting a beta particle. And if they emit a beta particle, according to Soddy's rule, you should remember that if you lose a negatively charged particle like the beta particle, then it represents like if you gain a positively charged nuclei. And therefore, what happens according to Soddy's rule is that you move to the right in the periodic table. So it's like if you gain +1 in the atomic number. And then we can resume like all this process with the case of oxygen. So if you start with an oxygen 18 and you make it react with a neutron, with one neutron, you will produce oxygen 19, which is a radioactive isotope of oxygen that starts to decay and produce a beta particle. After this beta particle is emitted, then what you will obtain at the end is fluorine 19, which is a much more stable isotope than the oxygen 19. And then this is the process how this neutron bombardment operates. By using this technique, then in 1940, for example, Edwin Mathison Macmillan and Philip Abelson, they were able to synthesize transuranium elements, like for example, neptunium with atomic number 93, or in 1941, they also produced plutonium 94, and later, during the next 10 years, all the other elements were so produced. So what you find in the periodic table from uranium to atomic number 103. And in this part of the periodic table, you will find the names of some of the scientists that we have discussed during our previous sessions. Like, for example, you will start to find curium or einsteinium or fermium or mendelevium, and all these names of the chemists and physicists who contributed to the development of the atomic models and atomic theory. Finally, we will talk about the discovery and development of nuclear bombs through the discovery of nuclear chain reactions. And to discover this process, we should talk about one of the first experiments made by Fermi, on which he did a neutron bombardment of uranium atoms. And he thought that in this experiment he had produced uh, a new element, a transuranium element with atomic number 93, but he was not able to separate this element, what he had produced or what he thought he had produced. And later, there were two chemists, Otto Hahn and Lise Meitner, who treated the bombarded uranium with barium because they suspected the production of radium, like the source of this radioactivity after this treatment. However, they failed in the separation, so they did a treatment, a chemical treatment with barium, because they knew that radium and barium, they should react in a similar way. So they tried to separate it and treated the sample like if it was with barium, but they were not successful in the separation. And they thought that what if the product of the reaction was not an element with atomic number 93 as suspected, but what if it was something else? What if it was barium itself? So, and they speculated this first because in order to try to explain why it was not possible to separate the element. So they had a treatment, a chemical treatment with barium, and from this product, from this precipitate, they couldn't separate anything. So they just got barium there. So they started to think about that possibility, but at the time it was very challenging because to this time, all these nuclear reactions involve the change of only one or maximum two positions in the periodic table by gain or loss of protons or by emission of alpha particles, like what we discussed before. But in order to change from uranium to, barium, it implies that there is a change in 36 positions of the periodic table. There's a difference of 36 in atomic number. So this is a very risky statement. And let's say that it was left just for an internal discussion, but it was not published. So at this time, it was the Second World War, and Meitner, she was a Jewish physicist, and she had to escape. So she was living in Austria, but she had to escape, and she moved to Sweden. And it was there in Sweden when she decided to publish the process about how it's possible to explain that from uranium you can get two barium atoms. And she was successful at explaining this process. She developed her theory and published the paper. And immediately it got the attention from the physicists around the world, because it was not only that two bariums were produced, but the barium which was obtained after this so-called nuclear fission, this barium which is obtained in this division or after cutting the uranium, the content of neutrons is higher than expected. So when you grow in the periodic table towards uranium, which was the last or the atom with the largest atomic number at the time. So when you move in this direction, the ratio of neutrons to protons is higher, is increasing. So uranium has more neutrons to protons ratio than barium. And it means that when you produce this barium through this nuclear fission process of uranium, then it contains an extra neutron load, let's say, that is lost because the material is also radioactive, so it lost this neutron. And if the amount of uranium is enough, then this neutron is able to divide again or to induce nuclear fission of other uranium atom, and you start with a nuclear chain reaction. And the quantity of energy which can be obtained from such a process, it was never before obtained. So it was a enormous amount of energy, as you can see and expect, and yeah, you can visualize from the nuclear bombs themselves. Finally, with the discovery of the nuclear fission process, they started the race to produce the nuclear bomb. There was like a fear that probably the Nazi Germany, they were able to produce this bomb first. So the United States immediately put a great effort with scientists all over the world who contributed to the development of the nuclear bomb. And for the success of this project, there were some technological issues, several technological issues. But two of them are first, the consecution of a critical mass of uranium, uh, which was rare, but not only that, but even more special type of isotope, which is the uranium-235. And second issue was that of the moderator. So as we discussed with the work of Enrico Fermi, it is required a moderator to slow down the neutrons in order to achieve a more efficient nuclear reaction. But other issues were also there, like that related to the work with fluorinated compounds. And you can imagine, I mean, it was an enormous challenge at the time. But it was successful uh, in December of 1942 to produce energy through uranium fission, which is like the first, the main process which is required for the nuclear bomb development. And it was 3 years later, or 2.5 years later, in July 1945, that the first fission bomb exploded in Alamogordo, New Mexico. And after that, just some months later, it was produced two more bombs, and they exploded over the cities of Hiroshima and Nagasaki in Japan. But after the war, uh, this technology has been used not only for military purposes, like for example for supplying of energy of military machines or vehicles like submarines or ships, but also for civilian use, where nuclear reactors have been used to power houses, for example. But this is not all. So it was known that, okay, we have discussed already about the fission bomb, which is called also atomic bomb, but there is also another type which is even hundreds or thousands of times much more powerful, which is the case of fusion bombs. And in this process, what happens is that two light atomic nuclei, they join. But as you can imagine, the repulsion which is experienced by these atoms to each other caused by the electron cloud surrounding or around the atomic nuclei. This repulsion is enormous, therefore very high temperatures are required. This is the reason why the fusion bomb is used to reach those temperatures on which a nuclei of, for example, hydrogen and helium can do a nuclear reaction and produce what is known like the nuclear fusion. And in this case, it's possible to produce some of the most powerful bombs currently in the world, like for example the Tsar bomb, which is an example of the fusion bomb. And this